I'm live. All right. We're going to do the word problems. The next day or two. The next 2 days are weird. We got like tomorrow. I don't know how long that like senior walk is, but is it like all day or is it just the morning? I don't know. Seniors?
Just the morning.
It's until lunch.
Oh, it is 10 till lunch. So you guys are, well, tomorrow will just be a total, tomorrow's just a work day. The other class will be like 3 people in there, so. Anyway, I'm assuming most of you guys have not done all the basic graphing questions, but we've kind of covered the main ideas. So you'll have time in class to knock those out. Today I want to go over 5 and 6. So take a minute, read number 5, and just see if the statement of the question makes sense. Like, do you understand what it's asking you?
Second.
Some loud jingle jangles. Jingle jangling over there?
Yeah, it's like. Oh, this book is super cool.
Are there any questions on what the question is asking? Question about the question.
Yes.
Okay.
What is the height of point P as a function of time?
Yes, that's what it's asking. It's asking, can you write a formula? That would tell you the height of this point at any given moment in time, based on the fact that you know the radius and the thing is rolling, right? Here's a little bit of a trivia question for you. It's slightly related to this. Actually, it's moderately related. If you rolled this object and say you had a point painted on the circle, and you traced out the path that that point took, does anyone know what shape that would make?
A squiggly line.
That's if you only looked at the height, correct? But I'm saying if you actually traced out the trajectory of this point.
Can we do a Humpty Dumpty?
Exactly. That's very good. It would actually trace out a shape like this. Like it starts off here. This is not obvious, but no point on the circle ever moves backward as it rolls. That confuses some people. Because you're like, wait a second, when you turn it, doesn't that point move this way? But the whole thing is moving. So anyway, it would trace out a shape like, does that sort of make sense?
No, why doesn't it go backwards?
Because it's moving forward. The
No,
ball.
point, if you're just watching the point goes back.
Yeah, it's like saying you're under a bicycle. It's a good question. If you're under a bicycle and you're rolling along and you say you put a little sticker on one point on your bicycle wheel, thank you. One for Zerda, one for Zach. It says go immediately to the office.
Caesar,
I don't know what.
yes.
Yeah.
It's quarantine time.
Feel free to fill out my sheet. For the
Anyway, so you can try yourself with a bicycle wheel. You can, put a little sticker on one part of it, and you'll notice that it kind of follows a path. Anyway, it's called a cycloid. There's your trivia of the day. Cycloid. That's that curve. So put that away. Thank you.
Why is it on a Humpty?
Humpty Dumpty. Okay, so what we're going to do is not that. The question's not asking what shape does this point trace out. It's asking what is a function that tells you the height of this point as a function of time. So ultimately, yeah.
It's sine, because you mentioned earlier with the
There's going to be, yeah. Here's the thing, let's do the graph before we do the function. That very often is the way to do things. So let's say here's the height of the point, and here's time. So we're gonna fill this out with just some basic, I mean, it is math, but it's kind of just common sense. For example, what's the minimum height of the point? 0, assuming the ground is height 0, which was, seems pretty reasonable to assume that's going to be convention. What's the maximum height? 10. That's 10.
Oh, because
Because the radius is 5, so double the radius, that gives you height. Okay. Now the point starts at 0. Now if it takes 3 seconds, if it does 3 revolutions in 1 second, that's the question tells us. How long would it take to make 1 revolution?
1/3 second.
1/3 of a second. Do we feel okay about that?
Yes.
How about to do 2 revolutions? 2/3 of a second. And then when we hit 1 second, well, that means we've done 3 full rotations. And so this curve, here's one last thing. Which happens faster, to go from here to 1 centimeter higher, or to go from like here to 1 centimeter higher? As in which happens faster? Yeah. Going from here to 1 centimeter higher is a lot faster than going from here to 1 centimeter higher, because you have to travel a much farther distance to raise your height 1 centimeter. What that tells you is that this curve, it starts off with a not very big slope. If that makes sense. Here's another mathy kind of, but still kind of a common sense thing. When will this thing hit the 10? What time?
1/6.
1/6, half of a third, right? So that would be 1 cycle. April, where's your stuff? Could you go get it? Okay, so that's 1 cycle. We understand? Let's draw 2 more cycles. Close enough. Not too bad. Do you have any questions like right now? Makes sense, right?
Yes.
Okay, great. Now, as far as like what function makes this graph, that's not a very obvious question. So we're going to use a little bit of geometry over here to break it down. Okay. So there's no questions right now? So what I'm going to do is I'm going to say, imagine that this cylinder has rotated some small amount. Okay. Now it's confusing because I was just talking about how the point P is never going to move backward. But if I ignore the lateral movement, I can say that a moment from now, the P value might be somewhere like here. This might be the new P. That makes sense?
Well, I thought it doesn't go backwards.
Right. That's what I'm saying. It can be a little confusing, right? Because actually the whole circle would have moved forward. So really P would be like, right? Here's the circle. Okay. So a moment later, it's rolling. So it'd actually be a little bit more forward, right?
Yeah.
So the new P value would be here.
Oh, that's what you're saying.
But if I then freeze it in time and say, well, P used to be here and now it's here, I can analyze, I can talk about this
Okay.
angle.
Okay.
That makes
It's not,
sense?
the circle is going, not P going around the center of the circle.
Well, the cylinder is rolling, but if you think about it, rolling is the same as just this thing spinning.
Yeah.
If you're ignoring is that what you're saying?
Yeah.
So we're only looking at the height. So for that purpose, rolling and spinning are the same thing. Confused?
No, I got it now.
So time for the dreaded geometry. Okay, I'm really interested in this angle right here. All right, that angle. Well, and why do I care about that angle? Any of you guys think you know the answer to that? Why would we care about this angle? Assuming our goal is to answer the question. Well, what quantity depends on this angle? The height, right? So the height depends on that angle, and that angle depends on
The angle.
The time.
the angle does depend on the angle. That's a good tautology. The angle depends on the angle. The time. So how much angle we've rotated depends on how much time has passed, right? So the logic makes sense. The height depends on the angle, and the angle depends on time. Therefore, the height depends on time.
It's a scheduling thing, you have to like go talk about your schedule.
So, glad to have you back, Zerda.
We're solving for a right triangle again.
So yeah, what you have here is a right triangle. I'm going to draw it a little bit bigger over here just so we can think about it a little bit. How big is the hypotenuse of our right triangle? 5. So then how big is that distance right there then? Let's think about that.
2.5.
It will be 2.5 at a certain moment in time, but we want to be general and say, in terms of theta, how big is this? Let's do a little bit of mathy, a little bit of, you guys remember SOHCAHTOA?
No.
Okay, a little SOHCAHTOA time. I'm going to call this quantity y temporarily. How can I relate an angle to the adjacent side and the hypotenuse? Cosine. The cosine of theta would be y over 5. Are there any questions on that?
Oh, I see.
So therefore, how big is this quantity? If I multiply both sides by 5, I get this.
Is that it? Is that the formula?
Well, no, our goal is to get a function, the equation that tells us the equation of this graph. So we're not quite there yet. But we're getting there. Okay. So then how far is this? We just figured out this distance right here. That distance was 5 cosine theta. So how high off the ground is the point then?
5 minus 7.
5 minus this. We feel okay about that? So the height would be this distance, 5, minus that little distance, 5 cosine theta. Do we have any questions on that?
What's the height now?
Huh?
Is that it?
Well, this is a formula for the height of the point as a function of the angle that the thing is turned.
Okay.
Now that angle of the thing is turned depends on
Time.
time. This is a critical step here. Hint, hint. Who thinks, well, don't shout it out if you know it, because I want to take a second to think about this. what's the relationship between theta and time? There's going to be a t here. But we're going to put a number here. If it spins 3 times every second, then theta is what times t? So think about that for a second. Okay, here's another hint if you're a little stuck. What's 1 revolution in terms of radians? 2 pi. So when t is 1/3 of a second, what do we want theta to be? Well, we want it to be 2 pi because 1 revolution is 2 pi radians. So when t is 1/3, we want theta to be 2 pi. When t is 2/3, we want theta to be 4 pi, sorry.
6 pi.
And then when t is 1, we want theta to be 6 pi. So what number goes right here?
6 pi.
6 pi. So here's a really good place to assess yourself. What percentage of the way through the problem do you think we are? Think about it.
We're 50%.
Sarita says 50. Anyone else another guess?
25.
25.
Don't
That's
say
less
that.
close.
33.3 repeated.
We're like 99% of the way done.
I said knuckles.
We're pretty much done. Why? How are we pretty much done?
We almost have it.
Well, we have a formula for height in terms of the angle. If you know the angle, then the height is just 5 minus 5 times cosine of that angle. And now we also know how that angle really is just a multiple of time. So therefore, the formula is do we understand how we got from here to here?
Yes.
We
No.
were close.
What?
We were close.
You mean a moment ago? Oh, did you have like a pretty good guess on, just based on the look of the graph, because you thought of flipping it over?
Yeah.
5
Well,
minus 5 cosine of the x.
Well, that's pretty close, yeah. So did you know it was 5 minus because of the shape, is the way it was kind of like, you had to think of it being flipped and shifted? Are there any questions on this, the 6 pi? Where we got that from?
yes.
Okay,
Where did we get that from?
so when we knew, just based on the fact that it was given to us, that this is the rotational rate, right? Because something can rotate fast or it can rotate slow, right? This is rotating pretty fast, 3 spins per second, right? So what we know is, based on this number, that when t is 1, after 1 second, the thing is rotated 3 times. Now, how many radians is 3 rotations? 6 pi, right? So therefore, I knew I wanted a relationship here that when t was 1, theta would be 6 pi. That's exactly what we have. Another example is, let's say when t was 2. How many spins will this thing have made after 2 seconds?
12.
It'd be 6 rotations. I think you're thinking of 6 rotations is 12 pi radians. Right? So that's what you have here. If you plugged in 2 for time, you'd have 12 pi radians. So, cleared up?
Yes.
Okay, so let's do the next one. We're done with. Yeah, that's the answer to the question. Okay. Take a minute and read the next problem. It's a little bit the same, and it's also a little bit different. Okay.
Would you drive around a circle?
What's wrong with driving around a circular track?
You don't move the steering wheel.
You what?
You don't move the steering wheel, you just find the angle and then, that's the gas.
You just keep
I guess you
going
could do that,
forward.
yeah. You could do that, sure.
I think Bob is going to drive.
It's not an elliptical track because that would be a much more difficult math problem. So,
Put it on the seat and roll like we wanted to.
would it what?
And roll like we wanted to. But it's a track.
You could roll, that's a math problem, is you take an ellipse and you pick a point on the ellipse and you say we're gonna roll. Now, when you say roll, you need a great mathematician, what does that word mean? But yeah, roll the ellipse without slipping, and then what path does a point on the ellipse trace out? There's a whole bunch of problems, math problems like that, where you're looking for a locus of points that are like, yeah, say you take this shape and you, because you could even, how about this one? What if you roll a circle around another circle? Like, what if you have a big circle and you put a little circle and then you put a point on that circle and then you roll this circle around this circle? You know, the point would, you would trace out some kind of shape like this, but it's no longer technically a cycloid.
What if the big one was also rolling?
Yeah, you can do that. Exactly, yeah.
Pretty.
Or just rotate it. All right, so. Has everyone read the question and understood what it's asking?
Yes.
Okay. Here's a very simple question. What point of view is that diagram taken from? Above, very good. It's like a bird's eye view, right? So Bob has, there's a wall here, it's this north wall. Then there's a racetrack, okay? The racetrack has a radius of, what is it?
700.
700. Let's answer some really simple questions off the bat. And it says that the wall is 250, is it 250?
Mm-hmm.
250 units away from the north end of the track. You feel okay about all that?
Yeah.
How close does Bob get to the wall? What's the closest he gets? 250. Well, he's right here. He's 250 away. What's the farthest? What's his farthest point from the wall?
950.
1650.
Why? Oh, you gotta double that.
Yeah, you got 700, 1400, 250.
Yes.
Okay. And it says that it takes him to make one lap. One lap takes, what is it, 20?
26 seconds.
Okay. Okay. And it's going counterclockwise. So let's take a moment in time later. Let's look at a snapshot just a few seconds later when he's right about here. Okay.
Oh.
Do they really drive around circular tracks?
Who's they?
Drivers like Bob.
Bob, yeah. Bob's actually part of this league that they only do circular tracks. It dates back. It's like this purist thing. They claim that in the olden days it was all circular tracks. So they actually look down on like NASCAR and stuff. They hate F1. At least NASCAR, it's sort of circular. F1, they're just wiggling around.
Yeah.
Those people are, it's basically like heresy to them. Yeah. They're very traditional. Okay, so if this is 700, let's say this is some angle theta, same idea as before. I want a relationship between his distance from the wall and theta, the angle he is rotated. You guys can take a minute, see if you can figure this one out. I want like a little formula. The hint is this distance here is very much a point of interest. And we know the distance between these, right? How far apart are those? 950. You can figure out kind of a similar calculation to the last question. how far is this distance? And that would basically tell you what is this distance. Yeah, take a minute, see if you can get an expression. We'll check our answer in a minute. No Eddie today.
No, Edward.
Sad. Big sad.
Edward won't be here until like Wednesday.
Why?
They're quarantined.
Sick. Well, all right. Does anyone out there have an answer to this that they feel relatively confident with? Zarita, go.
700 sine theta.
That is a good answer for this distance.
Oh.
Like that, right? No, it's good. That's a good answer. So you guys hear what she said?
Plus 250.
Very close. Let's get this one first. Does everyone understand why this distance here, this little dashed, this vertical dashed line is 700 times the sine of theta? Everyone feel okay about that? Okay. Now you don't want to add 250 on because, by the way, there are some people confused about the general principle here. I'll give you a simple example. Let's say I'm in a room. Here's a room. Let's say the ceiling is 10 feet tall. Let's say Bob is 6 feet tall. How far is Bob's head from the ceiling? Right? You go the big distance minus the other distance, right? So same thing here. You'd say, well,
The big distance is 900.
the big distance is 950, and you are just subtracting away that smaller distance of 700 sine of theta. We feel all right about that? Okay, what do you guys think we're going to do next? Not yet. We could. I mean, you could draw the graph now, but I'm kind of zeroing in on this, right? Like what we do last time. What we look to replace?
The theta.
A theta. So in this question, how does theta depend on time? Let's look at that. How does theta depend on time? Well, here's the only mention of time in the question. So when t is 26, we want theta to be 2 pi, right? Everyone understand that principle? So when t is 26, that corresponds to one rotation, one lap, which is 2 pi radians. So what number has to go right here?
2 pi over 26.
2 pi over 26, very good.
Pi over 13.
Exactly, which, yeah, you can say, we can simplify that if we like. I really like this statement though, because that really makes it very, very clear where the 26 gets involved. It's just 2 pi divided by that period. So, but yes, we can certainly simplify that down. And so we're pretty much done. The formula is that the distance between Bob and the wall is 950 minus 700 times the sine of pi over 13t. Kind of a complicated formula, right? Maybe not.
It is
It is?
crazy.
Yeah. Crazy.
It's complicated.
When you said crazy.
Well, it's just an example of sort of a complicated formula, but the geometry behind it's actually fairly simple. Does connect quite a few things. I mean, if you don't understand radians pretty well, this part's extremely confusing. You gotta know your SOHCAHTOA a little bit. Okay, so what was the min value of D again? 250. The max value was 1650. there's sort of this is not an asymptote, it's just a sort of a, kind of a, by the way, what number is this right here? 950. So 950 is actually where we start, right? At time 0, at this location right here, right? What's our D value? Would be 950. And does this graph start by going down or by going up?
Definitely.
Starts by going down because Bob's going counterclockwise. So at the very big, at T0, he's actually traveling towards the wall. So that distance is decreasing. And let's draw this one cycle for now. One cycle. I'm just trying my best to keep it kind of symmetrical and stuff. What's this time value right here? 26 seconds. Very good. So this one right here, at halfway, where is he on the track right there?
He's on the upside.
Right there. He's made half of a trip. So he's now back to being 950 away from the wall. And then something like, when does he go here? Well, that point, his farthest corresponds to this. What's that for moon talk? It's perigee or apogee. I can't remember. Anyone know? Anyone in astronomy? Perigee.
I'm in astronomy, but I have no idea what that means.
No, I wish I knew what that means. It's okay.
Oh, I'll pull it up on Wikipedia then. It's when you're in an orbit, they have fancy words for the closest point and then the farthest point.
Oh wait, no, I've seen those words before. I didn't know they were related to that though.
So in reference to the sun, it's aphelion or maybe it's aphelion, I'm not sure.
Ophelia.
And then perihelion.
Mhm.
I always mix up which one's the closest.
I think it's Ophelion's the farthest.
Yeah, I want to say then apogee would be if you're orbiting Earth. You have your apogee and your perigee. Oh, we'll look it up here. Good old Wikipedia.
Yeah, spacing I got into. I had to do an orbit transfer, and it included words like that. That's where I remember it from. Yeah, that seems so much more simpler now that I've done that. But I only got it because it was in reference to space. I swear, I need space.
So this says, yeah, apogee is the moon being farthest away, and perigee is the closest. What's crazy is it's 405,000 kilometers to 362,000, so it's a very small difference. It's like a 10%. This is 10% farther away than this. Which I guess
Isn't it getting more distant though? Like
Huh?
the moon's like getting farther out of our orbit or coming closer. It's like
That was the opposite.